look at my y, Windows way. So there's a GUI called the CF tool, which is it's curve fitting tool. So you have, what you do is you just do CF tool like that, and it comes up like that. So did everybody see what I did? I'll do it again. So you just type in CF tool and then enter, and it will come up. Now, if you're talking to your GNDU computer science, you might have to talk to them, because if it doesn't come up, it just means they don't have it available. But you can ask them, and maybe they can make it available. Okay? So it's like a toolbox, but it's a curve fitting tool. All right. So then here's how you do it. So you need your so you have a custom equation or you have a polynomial. Now, I will do the custom equation tomorrow. For example, the custom equation could be the relogical equation for your shear stress versus shear rate. So today I'm making it simple, so I'll just do a polynomial. Okay, so polynomial, and then you see what I did here, degrees. So the degree means what is the exponent. So we're just going to do a second order, right? So let's do second order, and on the x, and second order on the y, right? So this is very convenient, okay? Now I choose, now what you do is make sure that you load your x data, your y data, and your z data, okay? And then I put in, so for me, my x data I called xp. My y data I called yp. So yp. And then my z data are zp. Okay, and it just did the fit, right? So let's take a look now. Okay, it gives you the coefficients over here. So see, it gives you these are the, hang on a second, coefficients, okay. So it gives you all the coefficients, and if I remember correctly, the last coefficient was not significant, right? So let me see, oh, right here, this one. This one was not significant, this P11. Okay, so everything else was significant. All right. So now let's take a look. So we do a second. So let's do this one. Bring it up. All right. Let's do view. Okay. File. Print to figure. So I print a figure. It's one way of doing it, right? So there you go. It's just what I showed you, right? And then you can do the view, camera, and then do the orbit. And there you go. There's my XP, my YP. Now, I haven't figured out, I don't know if you can use my code, or you just have to go into your code and put in the max, and it will find the max for you and tell you where it is. So this can be very helpful for your data, all right? And then later I will show you the custom equation. You can type in your own equation. So that's very nice as well. And yeah, okay, so any questions on the GUI? CF curve fitting tool. And I'll post my code tonight so you can get it off the Google Drive, okay? Let me see. This should be bigger down here. Oh, here it is. Oh, by the way, it has same, you see R squared, sum of squares, and root mean squared error, just the same as what I got. If you want this to get bigger, I think you just pull it down, yeah, like that, and then you can rotate this. See? So it's very convenient. This way you can look at your data. If you don't like the fit, you can change to another kind of fit. Put in your own equation or change the equation. And then here's a fit option. Also, if you want to see the residuals, you can do view, and you can do residual plot. Oh, well, let me show you a contour plot for, well, all right, I'll do residual. So here's the residual plot. Trying to make it bigger. Okay. Well, hang on. Let me do view, and I'll do main plot. Let me remove that for the time being. Now you can see the residual plot. See, so you can see what the difference is from each data point from the surface. Right? So that's nice as well. You can see where the largest residuals are and so on. And let's see. So I can do main plot. Now, let me remove the residual plot. You can also do a contour. You know what a contour plot is? It's circles on the surface that tell you constant height. Okay, so let me show you that. Contour plot is here. So that tells you where the constant height is. And let me remove it so you can see better. Main plot. Okay, so there's your contour plot. Allows you to see where the constant height is. And you can put both of them. You can do a surface and a contour below it. And let me see if there's any. Oh, okay. Let me remove that. Let's do main plot and remove that. And then you can do prediction bounds, but on a 3D it's difficult. So if I can put, hang on a second. View. Which one?
Oh, the different colors?
Yeah. It's just, that has to do with the contour. It's just showing you the color. So if it's, you can see it's blue at the bottom and it's yellow at the top. It's just, it's showing you the contour. Constant height. So wherever the height is, it's going to be, if the height is similar, it's a similar color. You see that? You see the blue is on the bottom? What's that? Oh, I think you can change it. So up here, if you do, see this? Contour plot. Okay, I thought I had a prediction here. Oh, okay, you can do a prediction, 95% prediction, but I don't usually use it for 3D. It's difficult to see. So you see it's got a curve above and a curve below. So it's better, I use that more for the 2D plots. Okay? Okay, any questions on this one? Okay, if not, I'm going to get to, okay, that's your example. Now I want to get into the, I need to get into the nonlinear parameter estimation. So this one, this is all developed by myself. So I've developed my own system, but I think it's quite useful. So let me show you how it works. So remember, for nonlinear parameter estimation, for nonlinear parameter estimation, you have to do iteration, right? You can't do just one time. You have to guess and go through. So here are my steps. So first of all, you have to know how to set up your sensitivity matrix. We talked about that some. So first you choose your model, right? then you have to plot your scaled sensitivity coefficients, and I'll show you how to do that. And then you have to have your standard statistical assumptions. I'll go over those. And then you have to have your choice of your nonlinear parameter estimation method. And then you do your inverse problem. Estimate the parameters. Okay? After you finish your parameter estimation, you do your statistical results and your residual analysis. So when I give a research talk and I write my papers, I always follow this. This is what I give for my talks. Also, in my class that I teach, every graduate student gets this on the first day, and I tell them, this is the outline for your talk. And then when I grade them, I have it right there, and I have number 1, 5 points, number 2, 5 points, like that. And I grade them like that. And if they're missing something, then they lose points. So they have to follow everything. Okay? And I tell them, this is how you should give a talk when you go to a professional conference. And you should write your papers like this as well. So let's go through the steps, right? Choice of the model, number 1. Choice of the model. So you have to decide whether it's going to be a differential or explicit. So the explicit was what we did just now, right, for the GUI. Now I want to talk about the sensitivity coefficient, which is d eta, d beta. So here's what the idea is. If you give a small perturbation in your parameter and you get a small response in your model, it's difficult to estimate that parameter. But if you give a small response in another parameter and you get a large response in your model, it's easier to estimate the parameter and it will be accurate. It'll be the most accurate, more accurate than the others. So I'm not going to get into this one just because of time, but let me go through this. I want to go to the next one. So you have to plot your scaled sensitivity coefficients before you do your inverse problem. It's a forward problem because you have to guess, or you have to make a reasonable guess of your parameters, and then you plot that. You plot your scaled sensitivity coefficients, and you use a forward difference. The forward difference is you just take the model minus, let me show you how this works. Remember I told you you're doing a small perturbation in the parameter. So we just do 1.001 perturbation in beta 1, and you keep beta 2 constant. You calculate your model, and the model will be slightly different. Then you subtract whether it's constant. So this minus this gives a small difference, and then you divide by that difference right there. And what that does, it gives you an approximation. It tells you how sensitive the model is to the parameter. And that's for beta 1. For beta 2, you do the same thing. You keep beta 1 constant. You do a small perturbation change in beta 2. You calculate your model, and then you subtract the model when there's no perturbation. And then you divide by that small perturbation. So now you can see how sensitive the model is. So let me show you that. Okay, here's a graphical. Okay, by the way, this H, that's supposed to be eta, but it didn't come up because of the font. So it should be eta. This should be eta, that should be eta. So if you don't perturb the parameters, you just hold them constant, this is your result. When you do a small perturbation on the second parameter, for example, then the eta is going to be slightly different. So then you subtract the two, right? So you take the upper one and you subtract the lower one and divide by this small perturbation. Okay, that would be your sensitivity coefficient. That's the difference, right there. That's my difference. That if you run your experiment, if you want to estimate beta 2. You need to run your experiment in this range. If you run your experiment here, you cannot estimate the parameter. If you run it only here, you cannot estimate the parameter. So this is where you want to run your experiments so that you can estimate your parameters. Okay? And that's the sensitivity coefficient. Now, what kind of insight? So what insight can the scaled sensitivity coefficient give you? Well, you can plot these before you run your experiment, and it will give you a guide as to running the experiment. So I usually tell the students that if you don't plot your scaled sensitivity coefficient, it's like, that's why you should plot these beforehand, especially for a nonlinear model. Now, why do I have a picture of this? I'll tell you this one. So the largest scaled sensitivity coefficient will have the smallest error. That will tell you which one's the most accurate. And if they're correlated, it means you're going to have parameter estimation difficulties. And I'll tell you, and then if you have a small scaled sensitivity coefficient, it means if it's less than 5% of the total, you probably can't estimate it, and you can just remove it. Now, why do I have that picture over there? Okay, so the picture is you're putting your computer together, and your friend is above, is helping you above. You're underneath, so you're looking up coefficients. That means you can't separate the two parameters. So then you tell your friend, hey, please pull only one. So then he pulls one, but it only goes like this. You can't see it. They say, what are you doing? That's like a very small scaled sensitivity coefficient. You don't know which wire he pulled. So you cannot estimate that parameter. So then you say, will you please stop fooling around and just grab one and pull it hard? So then he pulls it, and you see only one wire goes like this. And then you say, that's the one. Plug it in. That is like a scaled sensitivity coefficient that is large and uncorrelated. You can estimate it with high accuracy. Even accuracy of about 2 to 5% error. And that's what you want. So that's why we plot the scaled sensitivity coefficients. Okay, now I want to show you how, I'll give you some examples of scaled sensitivity coefficients. So if you go to, and these are all on the Google Drive. So I'm going to show you this one. Okay, let's look at the left. Let me see. Yeah. All right. So if we look at, these two do not have the same shape. If they have the same shape, then they're correlated and you cannot estimate them. Another way of saying it is if you take one sensitivity coefficient and divide by the other and you get a straight line, a horizontal line, that's correlated. Let me show you. So if I divide the x2, one x2 by x1, and if you get a constant, that means they're correlated, and that means the model reacts. It reacts in the same way to each sensitivity coefficient. If it reacts in the same way, then you cannot distinguish the two. Right? What we want is when one parameter, if the model reacts in a different way to each parameter, then you can separate them. Okay? So I want to give you one other example too. I can't show here. Okay, that's fine. Well, I can tell you. Do you remember? Just a second. Let me get back up. Does everybody know the story from Denmark, the Hans Christian Andersen, about the princess and the pea? Did you hear that story about the girl? The girl comes at night and knocks on the castle, and the mother and the prince are living in the castle. And the girl says, I'm out in the rain, and I don't have a place to stay. And on the baseboard of the bed. And then they stack 20 mattresses on the pea. And then they say, okay, you can sleep up here on the top of the mattress in our nice bedroom. So then, and that's it. That's all they say. They don't tell her what they did. They just say, okay, here's our bed. Please sleep on there, and we'll talk to you in the morning. So she sleeps there, and then the next morning they say, how was your sleep? And she says, it was terrible. And they say, why is that? And she says, something hurting my back the whole night long. I couldn't sleep. So it proved that she was a true princess because she was so sensitive to the P in the bottom. This is a famous fairy tale from, you can look it up. Actually, I have a picture of her sleeping on the... Okay, so I use that story to tell you, so the princess is like the model. Okay? She's the model, and she's very sensitive to the P. The P is like the parameter. So she's highly sensitive to the P. If a fake girl comes and says, I'm a princess, and then she sleeps very well, that's like a parameter that doesn't have any sensitivity to her, right? So she's representing the parameter that you cannot estimate. Okay, but in the other case, she's very sensitive. So we want to have the real princess to do, okay? So what you can do, I'm going to show you how to do this. You can take, when you plot your scaled sensitivity coefficients, you can just take this, divide one, you can divide one by the other, and if you get a constant, then you cannot estimate them. So let's take a look here. So on the first one, the very first one, the problem here is, if you take one and divide it by the other, you get a constant. Or another way of saying it is, I could take the bottom one, or let's say I could take the top one, multiply by a negative constant. Well, let me say it again. Okay, I could take the bottom one and multiply by a constant, add the two together and get 0. So that means they're correlated. You cannot estimate them separately. So that's not, you don't want that situation. If you go to the next one, it's the same situation. If you go to the next one, you see they have different slopes. I can multiply one by another number, a negative. I could take one of those, multiply by a negative, and then add them together and get 0. Or you could just take one, divide by the other, and you end up with a constant. Are you following my concept? See, the shape is the same. On this one, the shape is the same. They start at 0 and then they separate, but they're separating in the same way. So you cannot separate those two. Down here, same thing. Because one is 0, one is going up. So if you divide one by the other, you get 0. It's just a constant. So you cannot estimate those. Down here, the same problem. It's crossing at 0. You cannot estimate those. And on that last one, if I multiply the bottom by a constant and then add it to the top, you end up with 0. So you cannot estimate those, okay? So everything, and then I'll get the other ones. I don't have time for those. Let me keep talking about these. Let me see if I can reduce the. Yeah, it's. Okay. Yeah, here we go. Okay, let's look on this side. Let's look at this one here. You can see it's a different shape. If you divide one by the other, you don't get a constant. So you can estimate those two parameters. No problem. On the second one, what about the second one? You got one straight line and one going up from 0. If you divide one by the other, you don't get a constant. All right? So those you can estimate separately. They're not correlated. On the number C, this one here, this one, you cannot separate your parameters. But if you have to run your experiment long enough so that you get into this region, then you can separate. Helps. So that helps you there. Okay, on this one, same each other, then it's not good. On this one, it's okay because the crossing is above, so you can run your experiment at any point and you can estimate. But of course, the longer you run, the better because these are larger here. And then the same thing with this one. These two, you cannot, if you divide one by the other, you won't get a constant. And then finally here, this one comes down and goes above 0, so the shapes are very different. So these are linearly independent, which is good. Okay, so I'm just giving you an idea of how you look at your scaled sensitivity coefficients before you run your experiment. Okay, any questions, comments on that? Yeah.
If the sensitivity are constant, if it is correlated, then is there any other method to handle this?
So yeah, that's correlated. That's a good question. So if it is correlated, then there are different ways to handle it. So one way is if you can adjust your model. If there's a possibility of you adjusting your model, that's one way. Another way is what I call a workaround. So it's not the best idea, but I have done it just to get a decent answer. And that way is you hold one parameter constant to something that you know is reasonable, and you estimate the other parameter. And then you do it again. So you take one parameter and you hold it at different constant values, and every time you hold it constant, you estimate the other parameter, and then you plot So I've done this, and I published with Sunisa on this one because we had the same trouble. So you hold your beta 1 constant at different constant values, and every time you hold it constant, you estimate beta 2. And when you do that, you get a root mean squared error for your result. You plot the root mean squared error at these different values, and then you get a minimum, and you take that minimum, and that will be your beta 1. So that would be a beta 1 best fit. Okay? That's one way to do it. I call that a workaround. Then there's another way which I'm working on right now, and it's more sophisticated. So I'm hoping to work on that in the next year and get it done. It's called we can't get into it here, but it's called Tikhonov regularization, and the main idea is you take your sum of squares inside your code, and you add a small constant. You add a constant times the residual squared. So what that does is it prevents your sum of squares from being non-convergent, because you take your sum of squares and you beyond this course. I mean, that's something that we can discuss outside. Okay, it's a good question. So up to now, I've just done this one because I can do this fairly easily, but this is not ideal. This is more like jugar. Would somebody call it jugar? In English we say workaround or jerry rigging. So okay, so. But it's better than not having a result. Okay, so now I want to continue. Check my time. Okay, we have a little time left. And next is okay. Remember, I'm going through the steps. Step number 3 is your standard statistical assumptions. Why do I do this? Because after we finish our inverse problem, we're going to check each assumption and tell the reader what the result was. So you have additive errors, zero mean, constant variance, uncorrelated errors, and normal distribution. And I'm not going to talk about the 6, 7, and 8. That's a bit more advanced. Let's just stick to 1 through 5 for the time being. So why do we care about this? Well, the estimation problems are usually less difficult when you have the standard assumptions are true. Now, normally you don't have every assumption is perfectly true, so you have to use some common sense and just say it's close to being true or it's not close to being true. Okay, so now let's show this. Now I'm going to show you. These are your results. So when you look at your results, here's how you examine them. So the first one is additive errors. So additive errors look like this. So you plot your x and you plot your y, and they look like this. What that means is as the y value is getting larger, then your variance stays the same. It means the errors do not change with the value of y. They remain the same, which is typical in most of our experiments. This is a multiplicative error. You see the variance is small when the y is small, and the variance is large when the y is large. Now, when does this happen? It turns out this happens. Is anybody here a food microbiologist? Well, that's where it happens in the food microbiology. So if you've studied food microbiology, you know that they always take the logarithm of the microorganism concentration, right? Why do they do that? Well, because it's usually moving from 10 to the 8 down to 10 to the 2. And it avoids this problem. Okay, so that's why they do the logarithm. Then you don't have this. Instead, you have this. This is what you want. You don't want this. Okay, next one is, you can, if these are additive errors with y predicted, and these are multiplicative errors, you can see that they get big. Okay, so on the left side is good, on the right side is bad. Number two, all you have to do is find the errors. As long as the mean is close to 0, that's good. But if your total scale is 10 and your mean is 1, that's not good. If your total scale is 10 and your mean is 0.1, that's great, right? Because it's very close to the mean of 0. And then 3, constant variance of errors. You can plot your residuals versus x, and you can check the variance. Assumption 4 is uncorrelated errors. I'll show you what that means. So this means, are the errors, they should be random like this. They should be random. So one of the ways random means jumping back and forth, okay, across the 0 line. So the way you check for this is you check if the number of crossings, which we call runs, is the number of crossings greater than half the data. So if you have 100 data, you should have 50 crossings of the 0 line, which we call runs. Now here's an example of correlated errors. And these are real data from a temperature versus time. And that shows you the residuals are not, the residuals are correlated. Sometimes you can't remove that. That's just part of the experiment. But at least you should report it. And then the assumption 5 is a normal distribution. You can plot your histogram, okay? So I'm not going to go over this one. Let's skip these, and then I'll go to, okay, step 4, to choose which method you're going to use. So we typically use ordinary least squares. You can use an integral or differential. And then I'll give you an example. So here's the primary model, which is it's a exponential decay, okay, and then this is typical in food science, right? You have exponential decay, and then the rate, you have a rate that changes with temperature, and you want to estimate k, e, and y0. So y0 is your initial y, k is your rate, kr, and e is your activation energy. So you can integrate. This is another way of doing it. If you want to do the integral, see that I have the integral, meaning it's explicit. So it's exponential decay compared to before that I had the differential. Both of them are the same, but you have to tell the code what you're going to do. Okay, so I will show you. Yeah, so this is, probably can't. Let me show you. Just a second. Okay, let me show you some results. Let me tell you. Let's see. And then I'll get back to the code. So this is a result from exponential data. So here are your data. And this is the equation. We supply data there. This is my residual scatter plot. And this is my histogram. Okay, so you can also produce a histogram here. Now these are scaled sensitivity coefficients. I wanted you to see this. So you can plot this before you run your inverse problem. So if you look at that, you want to think about two questions. Number one, are the scaled sensitivity coefficients large? So when I say large, I mean compared to the total scale. The total scale is 100, from 100 to 0. So when I say large, I mean more than 10%. If it's under 5%, it's too small. So let's take a look on the Y0, which is the blue line. Would you consider that large? For the top one, the blue one. So what you do is you look at the maximum value. So you go up here. The maximum value is 100. 38 out of 100 is 38%, so that's large too, but it's not as large as the other one. Now, the second question is, are they uncorrelated? So what do you think? Look at those two shapes. Are they different or are they same? They're different. So then correlated or uncorrelated? So it's uncorrelated. So then can you estimate both parameters separately? Yes. So now, before I run the inverse problem, you should be able to tell me which parameter will have the smallest error. And the way you know that is, whichever parameter has the larger scaled sensitivity coefficient will have the smallest error. So which one is it? So it'll be the Y0, not the rate constant. It'll be, right? The top one, the blue, is for the Y0. The bottom one is for the K. And that's very common. Usually the rate constant is not the most accurate. It's usually the initial value. So if you go back to the model, you go back to the results, we should see that the percent 40, is that right? Yeah. 1 out of 40 would be what? That's about, that'd be like 3%, right? It's over 3%. So the top one is only 2% error. The bottom one is about 3%. So it shows you that the rate constant has a larger error than the Y0. Okay? And you can see that in the confidence interval too. The confidence interval is smaller on the top than the bottom. Okay? So the parameter with the largest scaled sensitivity coefficient will have the smallest relative standard error, most accurate. Oh, I forgot I had it right here. So 1.8 and 2.6%. Okay? So it's correct. And then I just did it again with the explicit. I can show this to you later. Okay, let me see here. Okay, so okay, so those are my steps. Now I want to show you. I'll just get started and then we'll have to finish this one tomorrow. Okay. So here's what I use to do the nonlinear regression. I use the n-lin fit. And I told you can also use the CF tool, right? So here's how you do it. Okay, so on the left side you have n-lin fit, and the way that you run n-lin fit is you put in your sensitivity matrix, X, you put in your Y observed values, and then you put in your function, and then you put in your beta 0, meaning your initial values for your betas. Okay, so that's what those are. And then the output is going to be your betas, your R, your residuals, your Jacobian. The Jacobian is another name for the sensitivity matrix. So it's the same. MATLAB uses J. I use X. It's the same thing. And I made a mistake when I said this. On the Enlin fit, when you see that X, that's actually supposed to be a small x. Those are just your X values. So it's not the sensitivity matrix. The sensitivity matrix is on the left side, which is the J. And then you get your covariance matrix and your mean squared error. So, okay, here's how you do it. So, I will give you an example. I think I'll give you an example tomorrow to show you how to do this. Yeah, okay. I'll show you how to do this, and then I'll show you how to do it in dfittool. Okay, I'll give you an example on dfittool. And what we can do is we can look at the rheology data tomorrow in dfittool, and then we could also look at the exponential decay data and see the results in the dfittool. Okay? So I guess we are getting down to the end. All right, so I can't really start something new because of time. Okay, any questions, comments? Okay, so then that finishes for today, and then Dr. Sogi is teaching at 2 o'clock, right? And then I'll continue this tomorrow. We'll look at some more nonlinear models, and I'll show you my code, okay? Okay, very good. We'll see you in the afternoon then. Thank you.